Hey everyone, Greg here. How are you today? It's a cool, cloudy, rainy fall day in Oregon, and want to talk about the central limit theorem today. So, got a few diagrams here for you, and we're also going to talk about statistical significance. So I'm just broadcasting from home here. Now, first of all, what is the central limit theorem, and why do we need to know how it works and what it will do for us? Okay, well, let's take an example. Now, let's start out, and let's say that I have my seniors at my high school. They've all taken the SAT, and I hypothesize that the mean SAT score is 800. I don't know what a SAT score is now since I haven't taken the SAT in 40 years, but let's just say that I hypothesize, my HO is that the mean SAT score of all my high school seniors, of which there's 400 or so, is 800. So let's say I have my SAT scores distributed this way. Now, if you take a look at this, the mode score is 700 and the mean is 800. So that must mean there were some people that got very high scores. So that's what's called a skewed distribution. Now, the first thing to know about the CLT is this. So I'm going to draw a sampling distribution below it. Okay? And the sampling distribution is what you did in the activity. Now, this represents the means of all possible samples of any size. And the mean of all those means of all possible samples is always precisely equal to the population mean. And one of the things that is counterintuitive about the central limit theorem that you should be familiar with is that even if the population is distributed non-normally, so it's not completely symmetric, the mean, median, and mode aren't the same, the mean is the sampling distribution, or the means of all possible samples, is normally distributed. And that's counterintuitive, and that's one of the things that I wanted you to see. Now, why do we need to know this? Well, first of all, let's say we hypothesize that our mean SAT score is 800. So we set up a null hypothesis. My mean population SAT score is 800. Now, if this is true, then these are how all possible samples of, let's say, 10 sample means distribute themselves. So we have a sample size of 10. So if we were to take every different group of 10 seniors out of the population of 400, find that mean, and then put those means on a histogram, the mean would be exactly equal to the population mean. All right, so what can we do with this? Well, let's say then that we take a sample of our seniors, and we get a sample, and the sample mean is 750. Okay? So we take a sample, and we get a sample mean that's 750. Now, we were guessing that the population mean is 800. Well, here's the question. Could we have got a sample mean of 750 if the population mean was 800? And the answer to that question is yes, we could have. We could have just happened to get one of the samples that had a smaller mean. But here's the key. How likely is that? How likely is it that if the population mean were 800, we would get a sample mean of 750? It's not that likely, because it's at either end of the distributions of sample means. Now, here is what is more likely. It's more likely that the it's more likely that the sample of 750 came from this sampling distribution, which then came from a population mean, which was only 750. So yes, you could have got a sample that was 750 and it could have come from a population of 800, but there's not that many samples that would have a mean of 750. If the population were 750, there's a lot more samples that have a sample mean of 750. Therefore, it's a lot more likely that the population mean is 750 and not 800. And mathematicians have worked these probabilities out. So, if we pull a sample mean of 750 and it's statistically significant, then we can say, we can reject the hypothesis that the population mean is 800 in favor of the fact that it's not, because it's a lot more likely that the mean is less than this. And that's what the central limit theorem is important for. It's a pointer to a population parameter, and it allows us to gauge probabilities of what population means are based on samples. So the takeaway on the central limit theorem is that the mean of all possible sample means is always normally distributed regardless of whether the population is distributed normally or not. And that's the counterintuitive result that you could have got from that card activity. The second thing is the central limit theorem allows us to calculate probabilities as to what the population mean actually is. Okay, and all of inferential statistics is built off of that theorem. So that's pretty important to understand. I hope that clears it up a little bit. Okay, our next topic, we've got about 2 minutes here, is statistical significance. Okay, so let's talk about that. So let's say we got two groups of seniors, one from high school A, one from high school B, and we think that our null hypothesis is that the mean SAT score from both the populations is equal. So we hypothesize that group A is 800 and group B's mean is 800. Now we pull a sample. And it's very likely that the sample means could be 800 and 900. Now, if we pull those sample means and they're different by 100, can we reject the null hypothesis that the population means are equal? Well, there again, the laws of probability factor into this. Now, these two sample means have to be different enough to reject the null hypothesis that those population means are the same. So when you did that assignment, the p-value, which is the probability of committing a type 1 error, which is rejecting the null hypothesis when it's true, had to be lower than 0.05. And if that p-value is low, you know that the properties of those samples are such that there probably is not equality between the population means. So we reject the null hypothesis that the groups are equal in favor of the alternative, which is that they are probably not. Now, we're not sure they're not. So this is why we spent so much time setting up hypotheses. Okay, I hope that clears it up a little, and as we get more into next week, we'll work on this in a little more detail. Okay, everybody have a great afternoon. Bye.